Our first example today is to integrate x squared over square root of 25 minus x squared. Oftentimes when you have a square root of something squared plus or minus the variable squared, you want alarm bells to go off in your mind. That means you want to use trig substitution to help you do it, most likely. Not always. I mean, the first problem in the quiz was a memorized one. And if it's something squared minus the variable squared, you want to use sine theta as part of your substitution. But we got a 25 there instead of a 1. So we don't want just x to be sine theta, because that won't be helpful. We'll get 25 minus sine squared theta if we do that. And that's not 1 minus sine squared theta. It's 25 minus that. So we can't use the Pythagorean identity yet. But if we modify it a little bit and include an extra factor of 5 and let x equal 5 sine theta, then when we square that, we'll get 25 sine squared theta. And yeah, the 25 under the square root can be factored out, and we'll have a 1 minus sine squared in parentheses. But make sure you remember to compute dx. It would be 5 cos theta d theta. We will also need the fact that theta will be inverse sine of x over 5. We'll need that later when we replace theta in terms of x. Make all your replacements, make all your substitutions. The x squared on the top gets replaced with 25 sine squared. The x squared under the square root also gets replaced with 25 sine squared. Don't forget that dx gets replaced with 5 cos. If you forget the dx, you'll get the wrong answer. Square root of 25 minus 25 sine squared. The thing that makes this work is that can be simplified like this. That's square root of 25 times in parentheses 1 minus cos squared, which is 1 minus sine squared, which is 25 cos squared theta. Technically speaking, this is 5 times the absolute value of cos theta. However, as long as cos theta is greater than or equal to 0, we can get rid of the absolute value signs. Is that true? Is cos theta really greater than or equal to 0? Not necessarily. I mean, if the angle's down in the 3rd or 4th quadrant, then cosine of theta is negative. But we're kind of just crossing our fingers, hoping that it works if we get rid of the absolute value signs, since we dislike absolute value signs. And yeah, this is a situation where the ends kind of justify the means. We get the right answer in the end anyway, so we don't worry about it. If I make that replacement, then under the fraction there, that 5 cos theta will cancel with this 5 cos theta. It goes away ultimately, but I need it there so I can cancel it. And what's left over is integral of 25 sine squared theta. We've done this kind of a lot recently. Use integration by parts, or better, trigonometric identity. Sine squared theta is 1/2 minus 1/2 cos 2 theta. Cos squared is 1/2 plus 1/2 cos 2 theta. But it is a cosine in both cases. Multiply by 25, you'll get 25 halves minus 25 halves cos 2 theta. Now we can do that integral pretty quickly. 25 halves theta minus 25 fourths sine 2 theta plus c. But we're not done. Don't congratulate yourself too quickly here. We want to simplify this in terms of x. That theta right there just gets replaced by inverse sine of x over 5, so that's fine. But what about this part with the 2 theta in there? That makes it complicated. You want another trig identity. It's called a double angle formula. That's what's useful here. Sine 2 theta is 2 sine theta cos theta. Those are equal no matter what theta is. It's an identity worth remembering as well. So using the fact that theta is inverse sine of x over 5 now, this becomes 25 halves inverse sine of x over 5 minus the 2 will cancel with the 4, leaving a 25 halves. Sine of theta is sine of inverse sine of x over 5. And we also have cosine of theta is cosine of inverse sine of x over 5 plus c. Sine of inverse sine of x over 5 equals x over 5. At least for x over 5 being in the domain of inverse sine, which is between -1 and 1. And that will be the case as long as x itself is between -5 and 5, as it will be for this function. Cosine of inverse sine, what's that? Well, cos squared theta plus sine squared theta equals 1. So cos theta, if you solve for that, subtract sine squared theta from both sides and take the plus or minus square root, is plus or minus square root of 1 minus sine squared theta. Should I take the plus square root or the minus square root? Once again, we kind of just hope we can get away with the plus square root. I think what might happen actually effectively is in the case where the cosine is negative, yeah, you'd actually have a minus sign here, but ultimately you'd get a minus sign here too that would cancel and you get the same answer anyway. But I'll just think of it as the plus square root of 1 minus sine squared of inverse sine of x over 5. In sine squared of inverse sine of x over 5 is x over 5 quantity squared. As you take the sine of the inverse sine of x over 5 first, x over 5, and then square it. Basically, we're done except for some simplification. 25 halves inverse sine of x minus. This 5 can cancel with the 25 to leave you with a 5 halves. Yes, thank you. Yes. Yes, this should be an over 5 here. Thanks. Five halves times x. I canceled the 5 there with the 25. And then the square root can be simplified. You can write all this as one fraction under there by getting a common denominator of 25. This is x squared over 25. And then you could write this square root as square root of 25 minus x squared over square root of 25. And that's 5. And so it can cancel with this 5. Don't forget your plus c. And so in the end, it all simplifies to 25 halves inverse sine of x over 5. The 5's there canceled, minus 1/2 x square root of 25 minus x squared plus c. If we check this on Mathematica, Mathematica's answer actually looks different. How different? Let's see. We were integrating x squared over square root. I'll type it in like this, 25 minus x squared. This part looks okay, matching right here. But that part doesn't look so good. Arctangent, what in the world? Well, I did hint last time that you can write inverse sine of x over 5, for example, in terms of inverse cosine or inverse tangent as well. Because you could, well, might be simplest to imagine drawing a right triangle, labeling this angle theta, which is the whose sine is x over 5, sine SOHCAHTOA. Sine is opposite over hypotenuse. You could think of that side as x and this side as 5, and you could solve for this side as 25 minus x squared with the Pythagorean theorem. The tangent is opposite over adjacent, so you can take this over this. And that's kind of what's in there. Not quite. But yeah, some other simplification is going on. They are the same answer. They just look different. If we want to double check with differentiation, we can do that as well. My final simplified answer, take the derivative of 25 halves arc sine x over 5 minus x over 2 times square root of 25 minus x squared with respect to x and simplify. We do get the right answer for the original integrand. So my answer is correct. Next example we're going to integrate is 1 over x plus the square root of 9 plus 16x squared. Yikes. All right, you take a step back, you look at this and say, hey, that involves a square root of something squared plus, well, something involving a variable squared. This time it's a plus sign instead of a minus sign. I want to use tangent theta as part of my substitution, but how do I deal with the 9 and the 16? It's a bit tricky. The book suggested what to do for your homework today. I'm going to think of it this way. I'm going to imagine 4x to be equal to 3 tangent theta. Why am I thinking that way? Because if I replace 4x with 3 tangent theta, then when I square it and get 16x squared, I'll get 9 tan squared theta is what 16x squared gets replaced with. And then I see a plus 9 there. That would allow me to factor out a 9. That's what I'm thinking of by doing this. Alternatively, it's more natural sometimes to solve this for x and think of x as being 3/4 tan theta. Don't forget dx. Dx is going to be 3/4 secant squared theta, d theta. We will also have need to solve for theta. Theta is going to be inverse tangent of 4x over 3. We'll need that at the end again. All right, let's see what happens here. Replace x with 3/4 tan theta. That's this x right there. Gets replaced with this x. 3/4 tan theta. Then I get a square root of 9 plus 16x squared does get replaced by 9 tan squared theta. The 1 on top stays as it is, but the dx gets replaced by 3/4 secant squared theta, d theta. Yeah. One kind of nice thing happens. The 3/4 here in the numerator, so to speak, completely cancels with the 3/4 there. The square root of that is the same as the square root of this. And then square root of that is 3 times square root of secant squared theta, which is 3 times the absolute value of secant theta. Assume secant theta is greater than or equal to 0 to get rid of those absolute value signs. And something else good is that secant theta will cancel with one of those. So I changed the 2 to a 1 up there. But what's left over is still not so pleasant. What's left over is 1 factor of secant on the top and also a 3 tangent theta on the bottom, it looks like, if I have not made a mistake. I think we are good. You see something like this, looks pretty hard. It's probably typically better to get in terms of sine and cosine. Secant is 1 over cosine, and tangent is sine over cosine. And so it looks like, oh, I'm afraid something's wrong here. Feeling like maybe there's a mistake here somewhere, but I'm going to keep going. I'm a little unsure about the 1/3, to tell you the truth. This does simplify. The cosines cancel. You're left with the integral of 1 over sine, which is cosecant theta. And doing this integral involves a similar trick as my favorite trick from last week, multiplying by 1 in a disguised form, but a completely unexpected disguised form. Multiply this by cosecant theta plus cotangent theta over cosecant theta plus cotangent theta. I'll bring the 1/3 out in front, giving you cosecant squared theta plus cosecant theta cotangent theta on the top and cosecant theta plus cotangent theta on the bottom. This is just like last week. Let W be cosecant theta plus cotangent theta. Now, you may not have the derivatives of those memorized, and we don't test you on them on the Calc 1 gateway, but here's what they are. Just like the derivative of secant theta is secant theta times tangent theta, so the derivative of cosecant theta is negative cosecant theta times cotangent theta. And just like the derivative of tangent theta is secant squared theta, so the derivative of cotangent theta is negative cosecant squared theta. Probably didn't know that, but I'm telling you right now. So this becomes ultimately the 1/3 times the integral of, well, I'll bring the negative sign out in front, negative 1/3 times the integral of 1 over W dW. In the end, we get negative 1/3 natural log of the absolute value of W plus C. Replace W with cosecant theta plus cotangent theta. Negative 1/3 times the natural log of the absolute value of cosecant theta plus cotangent theta plus C. Not done yet, because we got to get it back in terms of X. X was 3/4 tan theta. Theta was inverse tangent of 4x over 3. Make that replacement. Negative 1/3 natural log of cosecant of inverse tangent of 4x over 3 plus cotangent of inverse tangent of 4x over 3 plus C. This one simplifies. Careful though, it's not the tangent of the inverse tangent, it's the cotangent of the inverse tangent. It simplifies to the reciprocal of what's inside, 3 over 4x instead of 4x over 3. What about that one though? It might be best to draw a right triangle. Imagine this angle to be theta. Its tangent is 4x over 3. Therefore, I could think of the opposite side as 4x and the adjacent side as 3. Solve for the hypotenuse by the Pythagorean theorem, get square root of 9 plus 16x squared. Cosecant is 1 over sine. Sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. This is square root of 9 plus 16x squared over 4x. And after those replacements, it'll be as simple as it can be. Wow. I won't bother rewriting it.